All right. Hello, all 10 of you, and welcome to Comp 3430 Operating Systems. It's almost like there's maybe an assignment or something due today. So yeah, I completely understand. There's some more people. Hello, other people. Welcome to Operating Systems. I guess not only is there an assignment due today, but it is freaking cold outside. It is so cold. So, and then there's a test. Do you have other tests today? No, okay. The test is on Friday. So if you're watching this from the comfort of your home, hello, but yeah, I completely understand. Let's get straight into it. Let's talk about operating systems. So what I want us to be able to do by the end of today's lecture is I'd like you to be able to write some code where processes communicate through message passing, specifically through signals. So we started this last class, and today I want to finish it. And the thing that I want to do really today is kind of like show how a parent and child process can talk to each other in terms of sending signals to one another. We've seen different processes and completely unrelated processes sending signals to one another, but today I want to spend some time looking at how related things can send messages with signals. And then we're going to move on to taking a look at pipes. I want us to be able to write some code that takes advantage of using pipes to send more complex kinds of information between processes. Pipes, we're going to see, are something that we kind of have to have a parent-child relationship with. It has to be something where we've caused a process control block to be duplicated, because pipes underneath behave like files. In fact, they look exactly the same as files as far as we're concerned. The main difference between pipes and files is that with a pipe, when I read from a pipe, it's a potentially blocking operation. Where when I was reading from files, we always get something back immediately because there's always something to read from the file. But with a pipe, we might have a pipe that's open with nothing to read from it yet, but it's not closed. There's still something that could be coming from this. So I want us to be able to do that. We're not going to talk about FIFOs before the test, and we're not going to talk about FIFOs before the break. But the sum of FIFOs really is pretty much a pipe. It's pretty much a pipe, and it's going to support the operation that you reminded me to take a look at last time, which was what happens if I try to read and write from the same file. A FIFO will enable something like that to actually happen kind of through the operating system. I also want you to be able to describe how the operating system supports and implements shared memory, which we're not talking about yet. We'll talk about that when we get to threads. Signals, we've talked a little bit about that, and I'd like to formalize some of this today in a slide. And finally, pipes. And like I said, pipes are going to be file-like things. They are file-like things where we're going to be manipulating our open file table, and we'll be adding things to our open file table that look and behave a lot like files in terms of stuff that we're able to do with them. The last thing is this kind of long-winded statement here. And again, the main thing here right now is synchronization. So we're going to look at how signals we can use signals to do something like more complex types of synchronization between a parent and child process or between different processes. We're also going to be thinking about synchronization in the form of pipes now. Again, these are file-like things, with the main difference being that when I call read on a pipe, there might not actually be data there, and read will block. Anytime we have a call that blocks, we're going to begin to think about this idea of synchronization. We're going to be able to guarantee the order of things happening in specific orders because of this idea of a blocking call. Last class, we were looking at signals. And the basic overall idea of working with signals is that our process will register a signal handler. Remember when we looked at the manual page, section 7 of the manual pages for signal, there's a whole long list of the different kinds of signals that we can send and receive between processes. But we can also register different signal handlers for signals. And we can do that either using the signal system call, or as we saw in class on Monday, the sig action system call. After we've done that, we basically just go off and do other stuff. So whatever other calculations we need to be doing in our code, Maybe it's just go to sleep for a long time and wait for some event to happen. And then eventually some other process is going to send us signals using either the kill system call or the kill command on the command line. Our operating system is kind of doing different things at each stage of this. So when I call this sig action or signal functions, what our operating system is doing is within the signal handling table, that list or table or array of signal handlers that we have for all of the different signals that we can receive, we're going to accept the request and then act on that request. Acting on that request, in our case, is changing the default action to be some function that's defined in the code space of this process that's running right now. So some function that we're going to be working with. We're going to take that function and we've accepted a pointer to it, and we're going to change the default value in that function, in that signal handler table, to be the function pointer. So this is ultimately what we're going to execute when we're sending this process signal. Then, after we've done that, schedule the process. You know, do other stuff here is basically let the process do whatever else it's supposed to be doing. Let it run code, let it spin in a loop and go to sleep forever. Let it run the stuff that it needs to do. Eventually, our operating system will receive this request to send a signal to that process. So either some other process is going to run the kill system call, or me sitting here at my keyboard is going to type in the command kill and try to send a signal to a process. And when I'm doing that, again, I'm not sending it directly to the process. I'm asking the operating system to send this message. I'm requesting the operating system send this signal to the process itself. Our OS is going to make decisions like, does this PID actually exist that I'm trying to send the signal to? And do I have permission? So I'm process 1 or process A here. Do I even have permission to send signals to this other thing? In a lot of cases, that's yeah, absolutely. But on cases where we've got systems like Aviary, we don't want me to be able to send SIGINT to your Vim session while you're coding up your exFAT stuff. That would be pretty bad if I was allowed to do something like that. And so our operating system has to make this decision. Does this process even have permission to send the signal in the first place? If it does have permission, then it's going to add a new stack frame to the process that's receiving the signal. And the stack frame is going to be what the signal handler is. So our signal handler stack frame is going to get added. We're going to run through the signal handler itself and then eventually return to wherever we happened to be before. So we do this context and mode switch to the process. The process starts running its signal handler. Eventually it returns, and where it returns is going to be wherever in its code it happened to be before, which is unusual because normally we're returning to a call site, but we're not returning to a call site, we're just returning to an instruction somewhere in the middle of this code section. I left us with 2 questions last time. The questions were, why did we not apparently be able to register a different signal handler for SIGKILL? So we were able to register a handler for SIGINT, and then I was hitting Control-C on my keyboard and it just printed out handling signal 2. But when I did the same thing with SIGKILL, I was able to register it, apparently. I was able to ask the OS to replace my signal handler for kill. But when I sent the kill signal, my process was terminated. It caused it to be terminated regardless of what I had set there. The other thing that we saw was that when we kept running kill on the command line to the same process, that process ID, the source of this thing, kept changing. And so why did it keep changing? I wanted to note here, because this came up in the second time I ran this class on Monday, that in Aviary, the arguments to kill are slightly different. So when I was typing kill, I was doing -sig whatever, but on Aviary, you will do just dash the process, the signal type that you want to send. So there's no uppercase SIG in front of that. So I want to hear, or I want to see some feedback from you about why we can't do these things, or what is the cause and effect of this. So my first one is, why can't we change the default action for sig kill? So our first response is here, because it's a privileged process, and what if some malicious process set the sig action for it? It will hog all the resources and other damage stuff, do other damage stuff. Kill is a program too, it has binary in use. Yeah, that's actually absolutely the answer. If I can register a signal handler for sig kill and actually, prevent myself from being killed, then I can do all sorts of cool stuff like mining Bitcoin all over the place. And then you can't stop me from mining Bitcoin. If I was able to prevent other processes and the operating system from terminating me, I can just take over the system and then never give up control of that thing. To protect the system's authority to kill programs, yeah, negatively affecting the OS. Too much plot armor for the process? Okay, sure, yeah. So we want to make sure that we can't allow other people to take over for us. Okay, awesome. So I'm going to go to the next question here, which was, I don't really want you to vote. There we go. Why does that source process ID change every time we run kill on the command line? We're running a program. Creates a new process. Yeah, absolutely. Every time I hit enter on my keyboard in my shell, new process being instantiated. Every time I hit enter on my keyboard, it's doing fork and exec. It's causing this duplicate PCB to show up, and then it's causing the code section of that new process to be replaced. And every time I'm doing this fork, I'm getting a different process ID. So kill is just a program. I'm causing this program to be run, and it's constantly going to, yeah, thank you, autocorrect, yes. It's constantly going to be causing this new process ID to show up. So every time I ran kill, it's going to be a different process ID here. Okay, awesome. Thank you all so much for participating in this survey. I'm happy to see your responses here. I want to finish up signals.c. And the way that I want to do this is I want to start adding some multi-process stuff. I want to add a fork system call to this to cause a parent and child to show up in this system. And then what I want to do is I want to send a signal from the child process to the parent using the kill system call. So if you want to follow along with me, and I invite you to do that, I'm going to pop over here, and I'm going to make this just slightly bigger. This is the interprocess comms Git repository that we started with last time. I did push some changes up to this after class on Monday, so if you want to follow along, Git pull this stuff. I'm going to do that right now. I am going to git checkout signal.c, and then I'm going to git pull. There we go. And I'm going to edit signal.c. So the place that we were at last time was that we'd added this signal handler here. And the signal handler was something that we had registered here on line 36 with sig action. We had to create this kind of complicated looking structure to be able to do that, but that's okay. In terms of building this structure up, it's kind of like look at the manual page and seeing what the description of the structure is. And it's annoying, but it's achievable to set this stuff up. And we get a little bit more information than what we would have otherwise been able to get. What I want to do now is I would like to cause a new process to be made using fork. So I'm going to do this. I'm going to say PID child PID is equal to -1 for now. So I just want to initialize this with something to start. And what I'm going to do is immediately after we do these registering signal handlers, I'll leave that sig action sig kill in there, but it has no side effect. It's not going to actually change anything. Immediately after this, I would like to do a fork. So I'm going to say child PID is equal to fork, and then I'm going to say if child PID is equal to 0, we're in the child process, Otherwise, we're in the parent process. So remember, this whole idea of fork is that we don't have one process doing both of these branches. We have two processes. The value that they each get back from this fork system call is going to be different in each of those different processes. We're ultimately running the same code section after that, and so those two different processes are going to take different paths through this same program. What I want my child process to do is I want it to do some really hard work. And the real hard work that this thing is going to do is go to sleep for 5 seconds. Yeah, it's going to do nothing. It's going to do, something. We're hand waving what something is here, but it's going to do some work. The goal that I have for this is that I want to be able to tell my parent process that I'm done my hard work, but I'm not finished yet, not exited. So I want to be able to give more granular control of this event has happened. So the way that I'm going to do that is I'm going to use the kill system call. Notice when I looked at the manual page for this, if we do just man kill, this brings us the program kill. This is the thing that we're running on the command line to send signals to processes. Here I'm running man section 2 kill. Section 2 of our manual pages is for system calls. Section 3 is for library calls. Section 1 is for programs that we have on the command line. We're taking a look at section 2 here, which is the system call for kill. And so what I'm going to do is I'm going to send a message to my parent process to say that I'm finished. My parent process, I know what its process ID is because before we called fork, I called getPID, and this is the parent process's ID. I'm going to add to this, and I want to show you another way we can get our parent process's ID. And I'm going to call this new variable parent PID. And what I'm going to say here is if I'm in the child, I'm going to say parent PID is equal to get ppid. So 2 P's here, get parent process ID instead of just get PID. I'll put a comment, my PID is going to be equal to this. We called get PID before fork. So the value that we have in my PID should be equal to whatever we're getting for this ppid. I want to send a signal to my parent. So parent PID is the second argument that I pass to kill. This is the PID. And then the signal that I want to send to it. So I'm going to send it sig int. I've finished this step. I'm finished this step, and you've registered the signal handler for this. Then what I'm going to do is I'm going to go and do some more hard work. I'll print F, finished telling mom about my hard work. I'm going to go back to sleep again. This time I'll just go back to sleep for 3 seconds to do some more hard work, and then I'm going to exit. So I want to do more hard work and then just finish in this program to kind of indicate, yeah, I'm completely finished now, I'm going to exit. My parent process here in this branch, I'm actually just going to delete this. I don't really need this else branch because the child never gets there. It exits in the conditional statement. Because I'm exiting in the conditional statement, we're never going to go past the end of this conditional statement, so our child is never going to see any of this code. The last thing that I want to do here is I want to change this behavior. I don't want to sit around spinning forever. I want to sit around spinning until my child has finished its first volley of hard work. And so what I'm going to do is I'm going to go back to the top of my file here, and I'm going to add a new file scope variable that's called flag. And I'm going to set this to 0 for now. When my child sends me this signal, what I would like to do is set my flag to 1. So I'm going to just change its value from this hard-coded 0 to a hard-coded 1. I am going to set the flag. I'm going to say that this thing has now happened. And then in my loop, I'm going to go back down here to the bottom, and I'm going to say in my parent loop, while not flag. So while this flag has not been set, please keep spinning. Just wait around for your child to finish that part of its hard work. So sit around spinning until the flag is set. Once that happens, what I would like to do is wait now for all children to finish, or wait for any child to finish. And we only have one child to wait for. We have just one. But this time I'm going to say wait null. So wait for that one last child to finish and then finally terminate. So I'm going to do printf here, waiting for child to fully finish. And then we've got one last print statement after the wait that says printf, all done, bye. Okay. So I'm going to make this code. I'm going to quit. I'm going to make. I'm guaranteeing there's going to be errors. I don't have a wait. So I need to do include syswait. I'm going to make this one last time. And I'm going to run signal. Stepping through this, what we're going to have is to get to line 50 here, and at that point, we're going to fork into two processes. We're going to duplicate our PCB. Once we've duplicated our PCB, our parent process, our child process is going to do hard work. I'm going to say here printf in child about to do hard work, just so we can see where we are. Make this one last time. Go to sleep, send a signal to my parent to say I'm done that hard work, and the flag should be set. Finish telling mom about my hard work, going back to sleep for 3 more seconds, and then exiting. Our parent process is going to sit around spinning for that whole 5 seconds while the child is doing some hard work, and then eventually it will try to wait for our child. Yeah?
The child process is sleeping, so like it could like make the entire thread sleep, right? So how would it write it to the standard out then?
So this part here, when we go to sleep like this, our print will have happened first. Going to sleep is then kind of caused this process to basically voluntarily block, but for a limited amount of time. So it's just going to sit here for 5 seconds and do nothing. Eventually then it will wake up. It will end that 5-second time-limited block and then start running code in its process address space again, and then send that signal. Does that answer your question? I may have misinterpreted what you're asking.
While the child is doing some hard work,
Uh-huh.
this would be like displaying the rotating
Ah,
screen.
yes.
So, but like the thread is sleeping, so it wouldn't sleep.
So remember that we've got two processes running here. They're both writing to the same standard output because that open file table has been duplicated. But just because our child process is sleeping doesn't mean that our parent process is sleeping. Our parent process is still fully running here. It's doing this micro sleep for 1/4 of a second every time it runs through this loop, but it's going to keep running instructions even while that other process is sleeping because we've duplicated it. There's two separate processes that are running here right now. Does that make sense? Okay. So I'm going to make this one last time, and I'm going to run it. So in child about to do that hard work, our parent process is spinning here. I finished. I'm telling my mom about my hard work. Our parent process says it's received signal 2 from that other process ID. It's waiting for the child to fully finish with this wait system call, and then finally it's printing out all done by. So this is cool. We're able to send some minimal amount of information between these two processes that are related to each other, but we're also able to send messages between these processes when they're not related to each other. So if I were to do something like this, start it, and then kill dash sig int 229230, it kind of forces us to change these states because we're allowed to send these processes signals from other processes. Again, provided that we have permission for that. All right, are there any other questions? Yeah. The parent process is kind of getting blocked in this loop, in that we're forcing it to block until that flag is set. So while it's actually running those instructions in that loop for quite a while, we're kind of saying that it's blocked at that point. It's never going to proceed until it receives the signal from the child process that it forked in the first place. It gets blocked again here on wait, because we're blocked until our child process exits at that point. So it does sort of block. This one doesn't really look like blocking here because it's not one of those system calls that we wait, but we've caused our process to block specifically because we're sitting and spinning around on that flag until it gets set. Yeah. So this is effectively a blocking operation until the flag is set. Okay. All right, cool. So I will put this up on that repository after today's class so that you have access to this code. One of the things that we can start thinking about here is one flag is a good example, but in reality, we might want to have many flags that we have set. This could be that we either have different signals that we're listening to, send me sig user 1 in this case, send me sig user 2 in this case, or repeatedly send me sig int. And each time I receive sig int, I will either change the value of the flag, increase it by 1, and then proceed to the next step, or I will have many different flags that I'm going to change their values for each of those. Okay, cool. So what I want to do now is start taking a look at this other structure. Signals are, it is kind of cool to be able to like send and receive these messages between these processes. But the main problem with them really is that we can't send stuff. I can send my parent process or some other process that happens to be running on my system an indicator that an event has happened, and we can both collectively agree previously that receiving this event has happened means a specific thing should start to happen. But I can't actually send stuff between processes. I cannot send you any bytes. All you can do is receive this signal to say that something is done. Pipes are file-like things. When we're working with pipes, we are working with something that looks identical to what it looks like when we're working with a file. Pipes are file-like things. We're going to call this pipe system call, and what we're going to get back from this pipe system call is not one file descriptor, but two separate file descriptors. When we call open, we get back a file descriptor for the file that we're working with. When we call pipe, we're going to get back two file descriptors, and we're going to give each of these two file descriptors a different name, but they ultimately refer to the same object internally in the OS. One of them is going to be the read end of the pipe, and the other one is going to be the write end of the pipe. I want you to imagine for just a second in your brains a literal pipe, an actual literal pipe. This name is a pretty good name for the abstraction that we're thinking about here. If we have an actual literal pipe like this, we've got a pipe that has two ends on it, and I can drop something in one end of the pipe, I can write something to it, and I can receive output on the other end of the pipe. I can read from it. This mental abstraction is pretty much what we're working with here. We have a write end of the pipe, I can send stuff to it, and I have a read end of the pipe, I can get stuff back from it. So I want to write some code to work with this idea. And what I want you to do is, if you've already got this repository, awesome. If you don't, then you can git clone it. The file that we're going to be working with here is called pipes. I've put a lot of stuff in here already because there's a lot of stuff that you should be able to do from something like Comp 2160, and it's not important for us to be able to see. Notably, I've written this function that's called split. Split does what you think it does in terms of Java's split on strings. It takes a string and it gives back an array of strings that are separated by a delimiter. If you want to read my code, you are very welcome to criticize it. This is not very good code, but it's here, and we're going to use it, and I'm not going to talk about what it does internally. What I do want to talk about is the idea of setting up and using these pipe structures. The very first thing that I've got here is that this is going to be a program that we're going to run called pipe. And what pipe is eventually going to do is take an argument on the command line of the program that it should run in a child process. The child process is going to read from standard input, but its standard input is going to be replaced with the read end of a pipe. And we, in the parent process, are going to send data through this pipe to the child process. The really important part about what we're going to do is that the child process is going to exec some other code. It's going to exec some other code that we have no control over, but we're going to replace its standard input, and it will just think that what we have given to it is standard input, like an actual keyboard on the terminal. So what we're going to do here in the very first case is we're going to call the pipe system call. I'm going to declare and initialize a variable, and I'm going to call it all pipes. This is going to be a 2-element array. We're going to pass this to the pipe system call, and the pipe system call is going to write the 2 file descriptors that it is giving us into this array. I'm going to go down here, and I'm going to do just that, pipe. And what I'm going to pass to it is all pipes. This is going to cause 2 new entries to be added to our open file table. One read end of a pipe and one write end of a pipe. So we'll get 2 file descriptors back, and that means that there's 2 new entries in our open file table to be able to work with. Immediately after I call pipe here, what I'm going to do is call fork. I'm going to say PID is equal to, I'm going to change this again to be child PID. Child PID is equal to fork. When I call fork, we're going to cause our process control block to be duplicated. Our process control block includes our open file table. So the open file table that we have in our process control block is going to get duplicated. So now we're going to have 2 processes that have both ends of this pipe open in their open file table. So duplicate our PCB, including the open file table. And the open file table includes both ends of the pipes right now, both ends of the pipe. Now I'm going to have this conditional statement again. So I'm going to have this duplicate process, and I need to do different things in each of the processes that I've got. So I'm going to ask this question: if child PID is equal to 0, I'm in the child. And I'm going to do the same thing here at the end of my child. I'm going to, for now, put exit success, so that everything that's outside of this conditional statement will be only executed in the parent process. In the child process, what I'm going to do is first, my child process will never write to this pipe. It's never going to write to this pipe. The only thing it's ever going to do is read from the pipe. And so we're going to close one end of the pipe that we're going to call the right end of the pipe. So I'm going to say close all pipes, and I want it to close entry 1 in all pipes. Close the right end of the pipe. I don't ever want to interact with that right end of the pipe, that thing that's going to have me dropping something through the pipe itself. Once I've closed it, what I want to do now is I want to manipulate my open file table. And I want to replace the entry for standard input, so the file number for standard input, and what I would like to manipulate it to be is the read end of this pipe. So whenever somebody in this process's space calls read on standard input file no, we're actually going to be reading from the pipe instead of standard input itself. The system call that I'm going to use to do that is called dupe2. Dupe2 causes entries in our open file table to be duplicated, and then it also replaces an existing entry in our open file table. So the first argument to dupe2 here is going to be the thing that I want to copy. And what I want to copy here is all pipe 0. I want to copy the read end of this pipe. And what I would like it to be written to is std in file no. I think this is entry 0 on the open file table. I forget what the actual number is, but I want to replace standard inputs file descriptor. So now reading from std in file no will actually read on the read end of the pipe. That's kind of cool. That's kind of cool that we can do this, but for what we've got right now, it's not really going to accomplish anything. I'm going to go back to my parent process section here, so outside of this conditional statement. And in my parent process, I'm going to say close all pipes 0. In the parent process will never read from the pipe. So I'm going to close that read end of the pipe. It's only ever going to drop the rock at the top of the pipe. That's the only thing that this thing is going to do. So I'm going to close that read end. And then what I'm going to do with this is I'm going to say in my parent process, while read standard in file no, this is in my parent process, and I did not manipulate the open file table for the parent process. The parent process is still reading the same standard input. It's still reading the exact same standard input than we had been working with before. I'm going to read from standard input. I'm going to read 1 byte. So I'm going to declare a new variable that's called byte. I'll be right back down there in a second. I'm going to say uint 8t byte. I'm going to read 1 single byte from standard input. While this is greater than 0, what I'm going to do is write to the right end of the pipe. Write the byte we got from standard in to the right end of the pipe. I'm going to write that byte, and I'm going to write 1 byte. This isn't going to do anything right now because all we've really done is say, hey, child process, change your standard input to be this new file descriptor, and then immediately exit. So it doesn't actually read anything. What I want to do with this child process is I want it to exec some code. So I'm going to say exec VP here. And what I've got up here just a little bit is I've passed to this split function the arguments that were in argv1. and I've put them into CMD args. So CMD args has now been split on white space for me. I'm going to say CMD args at entry 0. So that's the name of the program that I want to start, and then CMD args. So the rest of the arguments to this thing. If I get to this point, we have lost control because we just replaced our code section with someone else's code. If we get to this point, I'm going to say fprintf stderr failed to exec, and then exit failure. But we should never get to that point. We should never, ever get to that point. I'm going to make this one last time here. Whoops. I forgot a comma. I'm going to make this one last time. And I'm going to run pipes. And I'm going to pass it this argument as a second argument. I'm actually going to change this slightly. I'm going to pass it this argument as a second argument. Cat is this really cool program that reads from standard input and prints back to standard output. That's basically all it does when you don't pass it any arguments. So I can hit enter on my keyboard. And right now, we're kind of just stuck. We're blocked in two different ways. But if I run PSA here, what we can see is that we have this program called pipes that's been passed an argument of cat. And we also have cat running separately. So there's two processes. We forked, we exec'd this cat process, and now cat right now is waiting to read on standard input. It's blocked. So I'm going to start typing stuff in here. And where we are right now in our parent process is on line 77. We are blocked, waiting for input on the actual standard input. I'm going to type here, hello world, exclamation point, and I'm going to hit enter on my keyboard, and read in my parent process will become unblocked. I don't have the source code for cat to show you, but in cat, after we've called execvp, it is currently blocked on its own reads. It's sitting here waiting to read something from what it believes to be its standard input file descriptor. When I hit enter, both of those are going to become unblocked. This read in my parent will unblock, and it's going to start writing to that pipe, the bytes that it was able to read from standard input. Execvp here, again, we've lost control, so our process that we've launched, cat, has just read from standard input the stuff that was written to the right end of this pipe. I'm going to hit Control-C on my keyboard to terminate this process, and I'm going to instead now run this other program that's called tr. tr will take input on standard input, and then it's going to do replacement of stuff. So in this case, it's going to replace lowercase a through z with uppercase a through z. I'm going to hit enter on my keyboard. I'm going to run PSA, and now we can see that there's this tr process that's running. And if I start typing stuff in here, hello world, all in lowercase, we're going to unblock from line 77 in our parent process here and start writing those bytes out to standard input of tr through that pipe. tr is blocked on read. It's waiting around for it to get something written to that right end, that read end of the pipe, and it will get unblocked when I actually write stuff to it. I'm going to hit Control-C on my keyboard. And the very last thing that I want to do in my parent process here is I'm going to finish closing the pipe after we have no more inputs. And this is going to say, tell the read end, whatever process is on the read end, that there's no more input. When I call close on the right end of this pipe, whatever is currently blocked on the read end of this pipe will become unblocked, and the read call will return 0. There was nothing there. It got flushed, there was no input, no bytes were read. You should just finish up with whatever you're going to be doing. The very last thing I want to do here is wait for my children to finish. So I'm going to say wait null at the end of this. Wait for any child to finish. There was only one, so wait for that one to finish. And if I type in hello world here one last time, and then I hit Control D, now it's going to terminate this stuff for me. So closing that right end of the pipe tells my other process that it's all done. So the main things that I want us to be able to take away from this are that this system call here, pipe, changes the contents of our process control block. We're adding new entries to the open file table here. And the entries that we're adding to the open file table refer to the pipe entries that we've just created. We can only do this with processes that are related to each other. So this is something that's going to have to be coming from a fork system call. We have to have duplicated this process control block, including that open file table. Within each of the two branches, we're going to close one part of the pipe, one end of the pipe. And this dupe2 call and execvp here, these are working together to manipulate our open file table to replace the standard input file descriptor with this read end of the pipe so that whatever is launched by execvp will read from what it believes to be standard input, but actually get stuff from the read end of this pipe. All right, are there any questions about this? Okay, cool. So I'm going to pop back over here. At this point, you should be able to write code where processes communicate through message passing. So you should be able to write some code that receives a signal in terms of registering a signal handler, and then either receiving that signal from another program or from a child process. You should be able to send signals with processes, either by running the kill program or by calling the kill system call. You should be able to describe briefly how the operating system supports and implements signals. So this idea of having this signal handling table, what it does when it's actually, when the OS is receiving a request to send a signal to this other process. And then with pipes, what we should be thinking about here is we're doing file-like stuff. We're manipulating our open file table, and we're able to send things back and forth. Internally, our operating system is it's basically got a buffer. It has an array that it keeps track of the things that have been written to the pipe so that when it reads, when something else is calling read on it, it's going to get the contents of that buffer. We didn't talk about FIFOs. We may briefly talk about those after we come back from the break. There's still a couple minutes left in class. I'm going to go to this slide. And what I'm going to say is we've got a couple minutes left, so if there are any questions about the term test, I would be very happy to answer them right now. Yeah. Yeah, so the contents of the material that you can expect to see on the term test is up to today, with a strong understanding that you've had like 12 hours to think about this stuff, because I can tell almost all of you are still working on your assignments. And that's super okay. The strong emphasis on this test is going to be like file systems and RAID and journaling and file system checking and those topics that we covered before we started getting to this. Processes, that's something that we will have some coverage on, yes. Pipes, very, very little coverage on what we have for pipes. The final exam will be cumulative as well, and it will have more comprehensive stuff with pipes. Yeah. So that's a good question. Is it more from the readings or is it from the slides too? Both. Like in terms of some of the learning outcomes that are described in the course schedule, we didn't really necessarily talk about all of those in class. In the schedule, I've tried to list where you can find out more about those learning outcomes when we didn't necessarily talk about them in class, but there were also some learning outcomes that we only talked about in class. So things like choosing a RAID level for a certain situation, that's not really covered in the textbook, and that's something that we only did in class. So in terms of where you can find like what's covered about that learning outcome, I'd say look at the schedule and see what I've written there for each of the learning outcomes in terms of which chapter it's from or which class or whatever. I'm going to go to you and I'll come back to you, okay? Yeah. So like long answer, like an essay? Okay. Short answer to me is like fill in the blank and stuff. I'm not going to ask necessarily fill in the blank type questions. I might be asking you questions where you might need to like write a sentence or two. I'm definitely not asking essay questions because I don't want to grade essay questions. I really don't want to do that. Like I said in class, I'm also not going to ask you to do any coding stuff. I might give you code and ask you to tell me about what's going on in that code, but I'm not going to ask you to write any C code. Yeah. Yeah. Oh, okay, okay. Any other questions? All right, cool. Well, thank you all for coming out. I hope that you have a good rest of your day. I will see you all on Wednesday. I hope that you stay warm. I will see you on Friday. Yes, thank you. I will see you all on Friday. I won't really get much chance to talk to you, so I hope that otherwise you have a great reading week break, and then we'll see you all after the break. Bye, everyone.